There is a number. It is a specific, terrifying number that controls the fate of everything you have ever known. If this number were slightly higher, the stars in our night sky would have burned out billions of years ago. If it were slightly lower, atoms wouldn't hold together, and you, and the device you are watching this on, would simply dissolve into a fine mist of subatomic particles. Physicist Brian Cox calls the fine-tuning of our universe one of the most disturbing signals we have ever received from nature. Because when we look at the universe, the math doesn't add up. We are living in a reality that, statistically speaking, shouldn't exist.
When we think about the size of things, we tend to think of the size of things with reference to ourselves. So, the foot or the meter, or those things, or the inch or the centimetre, what are those things? Ultimately, historically, they're based on properties of the human body. So they're based on biology. And that's what we did historically, because why would you do anything else? Is that fundamental? Well, the answer is no. It doesn't tell you anything profound or deep about the deep structure of the universe. But of course, the history of physics tells us, as we go into the 17th century, the 18th century, the 19th century, 20th century, we then begin to understand that there are things that are much bigger than us and much smaller than us. We're looking, I suppose, for units of measurement that you could imagine if we met some aliens from some different civilization. They might not even have arms, right, or feet, but they might be very different in size and scale from us. So what would the common language be? Is there some unit of measurement that we could all agree on?
Imagine walking into a casino. You go to the roulette wheel, bet on red 7, and you win. Nice. Then you go to the poker table and get a royal flush in the first hand. Then you walk outside, buy a lottery ticket, and win the jackpot. You would be arrested immediately. Why? Because luck like that isn't possible. It implies the game is rigged. Well, according to modern physics, our universe looks exactly like that rigged game. Something is seriously off. The universe is hiding something from us. And the deeper we look, from the ghost of dark matter to the silence of the aliens who should be here, the stranger the answer becomes. Today, we aren't just looking at the stars. We are going to the edge of physics to find out why our reality feels broken.
Cosmology is terrifying. It raises questions. It makes vivid questions that we all have. What are we doing here? Right?
Yes.
So you try to link it to things that people think about naturally. And that's why people are fascinated by this stuff, because they do actually think about it. It might not be with the right names or the right words or the right facts even, but they're thinking about, how did I get here? How did I come to exist? What is the future? Do we have a future? What was our past? These are universal questions, I think. There is a central problem, though, which is still not solved, which is what lies at the centre of a black hole. Now, just in Einstein's general theory of relativity, actually, it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not, and is still not, understood. So that's a great mystery. And it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are. We have a problem with the singularity. We don't really have any access to it. We don't have the conceptual tools to explore it. So it may remain a mystery for a century to come. It's not clear what to do. The great revolution in black hole research was to notice, and it began with Stephen Hawking's work in the mid-1970s, was to notice that actually there are conceptual problems at the event horizon of the black hole. Not in this extreme place, not only in this extreme place, at the singularity, whatever that might be, but at the horizon. Now that was a real challenge and extremely interesting, because we strongly expect the laws of nature that we understand now, laws of nature that we have full mathematical and conceptual control of, to apply at the event horizon. And so that's why black holes have become so interesting. It's because we have a place where we think, we assume, and indeed we're right to assume, it seems, that we have full control of the physics. We understand what's happening, but there is a fundamental clash of principle between our two basic theories of nature, general relativity and quantum mechanics. And that is ultimately why the event horizon of a black hole and black holes themselves have become so fascinating and so important.
Einstein's theory of general relativity is our best theory of space and time. And so it really is, as we talked about before, it's you imagine space and time as a sheet. Just imagine it as a thing, sort of literally a sheet, surface. And all the theory says is that if you put matter and or energy into that, then it curves it and distorts it, and it can stretch it and make it shrink. And so it's the response of space and time to matter and energy. The simplest version would be the sun. So you put a big spherical ball of stuff in there, and it warps space and time such that the nice straight lines, something just travelling, minding its own business through that warp space, turns into an orbit.
And that's why you can actually kind of see things that are behind the sun?
Yeah.
Okay.
So light bends around the sun because it's just travelling through the curved space. The Earth goes round the sun because it's just rolling, minding its own business through the curved space. So an example would be, you might say, well, how does curved space, can that give rise to something that looks like a force, which is gravity? So the best analogy I know of is to think of walking around on the surface of the Earth. So if you stand on the equator of the Earth and you with your friend and you say, we're going to walk due north. So we're going to set off, let's say we're 1,000 miles apart on the equator and we're going to walk due north. And what's going to happen? So you walk in straight lines. You don't change direction. You don't do any accelerating. But the straight lines are the lines of longitude on the surface of the Earth. So as you go further and further north, you get closer and closer together. And if you carry on to the pole, you bump into each other. But nothing's happened. Right? There's no forces acting. It's just that you're moving on a curved surface. And so you get closer. And that's basically Einstein's theory of general relativity. So all you have to do, so that those folded kind of geometries, is you have to try and specify where you would put the matter and what kind of stuff you'd put there to make the geometry fold in that way. And you can do it. So you can write down that geometry. It's called a warp drive geometry, I think it's called. It's in textbooks. So you can do that to have a warp drive. The question becomes, what sort of stuff would you have to actually put into the real universe to make it warp in that way? And it usually turns out that it's the kind of stuff that doesn't exist, right? But it has properties. It's sort of matter or sort of energy that has properties that do not exist in nature as far as we can tell. But you can still write the geometry down in Einstein's theory.
So if you had significant
stuff,
force or mass or whatever it is, if you had that stuff that doesn't exist, it is a concept that
so the geometry exists. So you can do it, and you can do the calculations, and you can see the warp drive. You can construct wormholes that connect distant regions of the universe, which you could use as time machines. You can do all that in the theory, but in nature, you'd have to have the right stuff to do it.
But that stuff is not real.
That seems to be
as far as we know.
Yeah.
Now, what would have to happen? Like you would have to have enough power or mass to be able to fold those two things together?
It tends to be weird stuff, like stuff that has a negative pressure or something like that. So stuff that has physical properties that are just bizarre, and that no matter or energy that we know of in the universe has. So that to make the geometry happen.
But it's conceivable in theory that this could exist, even though it doesn't.
If you had a wormhole, then what would happen if you tried to travel through it? And what seems to happen is that they become unstable the moment that anything tries to go through. So you get kind of a feedback of stuff going through and through and through and through, and so it collapses. And there's a great book by Kip Thorne, actually. We just mentioned him. He got the Nobel Prize last year for the gravitational waves, and he wrote a brilliant book, I think it's in the 80s, called Black Holes and Time Warps, where he talks about the answer is we don't fully know. But most physicists think that even if they existed, they would be unstable. And as soon as you even tried to transmit information through them, send a bit of light through, then there would be this sort of feedback and they'd collapse. And ultimately, the reason we don't really know absolutely is because you need what's called a quantum theory of gravity. And we don't have one. So we don't have the theoretical tools to be absolutely sure that these things would be unstable or don't exist in nature.
What are your thoughts on life outside of this planet?
I think there must be. Even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water.
Like Europa.
Yeah. And the reason is, if you think about, the reason I think that, and it's a guess, is because if you look at the history of life on Earth, then so Earth formed, and it was just there was no life. It was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry, became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. I mean, the other option is it came from space or something like that, but it probably didn't, right? It probably began on Earth. So that means that at least here, that happened. And that we know that the conditions that led to the origin of life on Earth were present on Mars 4 billion years ago. And we know that they're present on Europa today. So I don't see that there's anything special. Life is just chemistry. And the idea that geochemistry becomes biochemistry is not fanciful because it happened here. So I think that given the same conditions, it would be surprising to me if the same thing didn't happen, in that life begins. To test that is one of the great frontiers of science now. It's one of the great challenges, which is why another reason we're interested in Mars, because we know those conditions were there. We know there were what's called hydrothermal vent systems on the floors of oceans on Mars 3.8 or 4 billion years ago. So it would be good to know if what I've said is right. And the way we find out is to find life or evidence of past.
And Earth-like planets exist just in our solar system alone?
In the galaxy, 20 billion, something like that. It's 1 in 10 stars.
So the odds of complex life out of our incredibly fortunate situation, but the odds of that occurring on any of these billions of other planets that exist?
We don't know. Our species has been around, a 250,000 years or something? So it's just now, basically. So let's say 4 billion is on the fortunate side. Let's say that it was double that or triple that on the average. Suddenly, that's the age of the universe, right? And that's a third of the age of the universe it took. So how many of those worlds have been stable for 3 or 4 billion years? That's quite a tall order, actually. It looks like our solar system might be quite unusual in that respect, because the planets got to remain stable in a stable orbit. The stars got to remain stable, at least in our solar system. Large moon stabilizes. Jupiter plays a big role. It's very hard to explain the evolution of our solar system So when you do computer models of solar systems, you don't tend to get 4 rocky planets too close to the sun and 4 big gas giants further out. And one of the current best theories, and I say this because it shows you how lucky we might be, is that Jupiter, they tend to form these big gas giants and migrate inwards towards the star. So in almost all the computer simulations, just because you've got this big gas giant orbiting in all the dust around the star, they tend to drop inwards. And it looks like Jupiter did that. So it looks like it formed and came in almost to where Mars orbits today, and cleared out the region around Mars, actually, which is maybe the reason Mars is so small compared to to Venus and Earth. But then Saturn was coming in as well. And in the computer models, the interaction between Jupiter and Saturn stops Jupiter coming in before it gets to the Earth. And they both get dragged out again. And so to where they are today.
Oh, wow.
And so that seems to be, it's one of the best theories for the evolution of our solar system. So what are the chances? The chances of that are so minuscule, tiny. So that's the thing I think about these rocky planets. In order to get a civilization on them, I guess you need quite unusual solar systems. And that would be a guess. And you need quite unusual stability on the planet for billions of years. And that's why I think we might be quite lucky.
How does Bode's law work? Bode's law is a method of detecting, if you look at the mass of a planet, you can accurately detect how much mass and the size of a neighboring planet.
I think, wasn't it just the positions of the orbits? I think.
Right, where it is.
Yeah. And it's one thing that is true about our solar system is that if you get the computer simulations, you can't put more planets in. So if you try and put more planets in, it becomes unstable very quickly.
So the mass of, like, if you measure Mars, you can accurately depict where the next planet close to it would be?
It was. I mean, it was. That's what was done. Was it 17th century or something? I can't remember. It was long. Yeah, and it was just one of those things where you notice a pattern.
Right. They were just trying to figure out what the
so it's just a pattern, which is there's nothing to that really. Other than to say that most simulations of the solar system, if you put other planets in, they tend to get thrown out by gravitational interactions. So there is a sense in which our solar system has got as much stuff in it as it could have. So the planets are nicely spaced. And you're right, given the mass of them, that depends on how close another planet can be before the interaction goes wrong and it gets thrown out into the intergalactic space or something, because planets do that. We know that planets get thrown out of solar systems by gravitational interactions. It points to the fact that solar systems are not stable over long periods of time. They're not like clockwork things. They're not like Newtonian clockwork and it just goes on forever. They're not like that. They evolve, and planets can shift orbits and change. If you look at the surface of the moon, for example, it's covered in craters, and that was caused, they all seem to hit about the same time. And it's about 3.8 billion years ago or so. And that's called the late heavy bombardment. So we know that if you look at cratering rates on Mars and on the moon, it all seemed to happen in this, not all, but a big peak around that time. And that seems to be correlated with Neptune moving outwards in the solar system and into Kuiper Belt, basically, or towards the Kuiper Belt, and causing all sorts of havoc, and everything comes into the inner solar system. So those things happen. But it didn't happen when life was established on the Earth.
How long has the solar system been in this particularly stable situation that it's in now?
It's since about 3.8 billion years ago. So if it had been unstable at any point since then we likely wouldn't be here.
Right.
So we want to know with a Higgs particle, we know what it does, which is it gives mass to everything. So it's fundamentally the thing that gives mass to all the other things in the universe at the most fundamental level. So electrons, for example, and the up and down quarks, they get their mass from their interaction with the Higgs. That's why they're massive. That's another reason we exist. We go right back. We wouldn't exist if there wasn't mass in the universe. And the Higgs is ultimately responsible for that mass. I keep caveating it because then you get other sorts of mass that are generated, but that the fundamental basic seed, as it were, is from the Higgs. So what we want to know how that thing behaves. So you want to study it. So you want to make a lot of them so you can take a lot of pictures of it and study it a lot and see exactly how it does that. And so that's what we're doing. That's what we're engaged in at the moment. We're making high precision measurements of the way that particle behaves so we can understand the laws of nature. I mean, that is the laws of nature. How are those particles behaving and what are they doing?
But it is possible that some new form of particle, something else could be discovered.
Yeah.
That we don't know about yet.
Because we almost know, that there are other particles out there in the universe.
We almost know?
So a thing called dark matter.
Yes.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle, that fits beautifully. And we see lots of different observations of the way galaxies rotate and interact. And even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. And I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC.
Do you think that it's possible, do you ever entertain the idea that it's possible that we are the only intelligent life in the known universe?
I tend to restrict myself to the galaxy.
Right.
So I do think it's possible that at the moment there's one civilization in the Milky Way, and that's us. And I think that's important, actually. And it goes back to what I was saying at the start about the astronomy and cosmology being part of the framework within which you have to think. If you're looking for meaning, or you're looking for how we should behave even politically, that has a bearing to me. I mean, imagine that we're the only place where there is intelligence in this galaxy. And how should we behave?
Right.
Should we actually, notwithstanding the fact that we're tiny and fragile things and insignificant physically, should we consider ourselves extremely valuable in that respect? Because I would go as far as to say there would be nowhere else where meaning exists in the Milky Way.
Meaning.
Because meaning is one of those things that scientists don't talk about very much, although Richard Feynman, one of my great heroes, did talk about it. There's a quote where he says, "What is the meaning of it all?" It's a great essay called The Value of Science. And so what is self-evidently true is that meaning exists here because it means something to us. So that's kind of an obvious statement. Your life means something to you and me, and so meaning exists. But I think it is a local and temporary phenomenon. I think it emerges. Meaning emerges from configurations of atoms, which is what we are. We are simply that. We're nothing more than that. We're very, very rare configurations of atoms, I think. And so that means that we are, if you go all the way down that line of logic, we are the only island of meaning in the galaxy.
Meaning only to ourselves.
Yeah.
It means something to us because we're the only ones who can grasp the concept. And we are finite. We are a finite organism. We have this temporary existence while we're here. And to us, there is meaning.
Yeah. And I don't know any other way to define it.
Right.
So I'll define it like that.
Yes.
I don't think there's global, otherwise you have to believe there's some kind of global meaning and that's a God type thing. And I don't think I think it's more wonderful and more challenging to us, because we have to take responsibility for it, to say we should operate such that we are it in this galaxy. There's nothing else. I'm sure there are other civilizations out there in the universe, because there are 2 trillion galaxies. I just can't believe this hasn't happened in other places. The question is, how often does it happen, and how widely spaced are the civilizations?
The dials of reality. Let's start with the most uncomfortable fact in science. You exist. That shouldn't be possible. When physicists strip the universe down to its basic code, they find about 30 fundamental numbers. These are the constants of nature: the speed of light, the mass of an electron, the strength of gravity. Here is the scary part. These numbers are arbitrary. There is no underlying law that says gravity must be this strong, or that electrons must weigh this much. It's as if someone sat at a giant mixing board at the beginning of time and turned 30 different dials to random settings. But if you change any of these dials, even by a fraction of a percent, the game ends. Take the strong nuclear force. This is the glue that holds the nucleus of an atom together. It binds protons and neutrons. If we made this force just 2% stronger, the sun would have burned through all its fuel in a few million years, long before life on Earth could evolve. The universe would be a flash pan of exploding stars, leaving nothing behind but black holes. If we made it 12% weaker, the elements essential for life, carbon, oxygen, iron, would never have formed. The universe would be a dark, empty soup of hydrogen gas forever. And it gets more precise. Sir Roger Penrose, a colleague of Stephen Hawking, calculated the probability of our universe starting in a state that allows for life. The number he came up with is so large, the human brain cannot comprehend it. It is 1 in 10 to the power of 10 to the power of 123. If you tried to write that number out, putting a 0 on every atom in the observable universe, you would run out of atoms long before you finished writing the number. It is effectively 0. So, why are we here? And Brian Cox suggests there are only 2 possibilities, and both are equally terrifying. Option 1. We are incredibly, impossibly lucky. We just happen to be born in the one version of reality where the math works. We are the lottery winners who don't realize how close we came to never existing. Option 2. We aren't the only universe. This brings us to the multiverse theory. Imagine a bubble bath. Each bubble is a separate universe with its own laws of physics. In bubble A, gravity is too strong and the universe collapses instantly. In bubble B, gravity is too weak and nothing ever forms. But in our bubble, bubble C, everything is just right. We aren't special, we're just the survivors. But if that's true, where are the other bubbles? And what happens if they touch ours? The worst prediction in history. If the fine-tuning of gravity makes you uneasy, wait until you meet the cosmological constant. This is the energy of empty space, and the energy of nothing. Quantum mechanics predicts that empty space shouldn't be empty. It should be fizzing with energy, particles popping in and out of existence. So, physicists calculated how much energy should be in empty space. They did the math. They checked it twice. Then, astronomers went out and measured the actual energy of empty space by watching how fast the universe is expanding. The 2 numbers should match. They didn't. And the theoretical prediction was larger than the actual measurement by a factor of 10 to 120. That is a 1 with 120 zeros after it. This is widely regarded as the worst prediction in the history of physics. Imagine you estimated the distance from New York to Los Angeles. A bad guess might be off by a few hundred miles, but an error of 10 to the power of 20 is like estimating the distance to Los Angeles, missing by more than the size of the entire observable universe. Brian Cox has pointed to this discrepancy as a smoking gun. It means we are missing something fundamental about reality. The vacuum of space isn't what we think it is, and this leads to a terrifying concept called vacuum decay. Because our measurement of the vacuum energy is so weird, some physicists suspect that the universe isn't in its true lowest energy state. We might be in a false vacuum. Think of a ball sitting in a valley. It's stable. But what if there is a deeper valley right next to it, separated by a thin wall? If the universe ever tunnels through that wall, a bubble of true vacuum would form. This bubble would expand at the speed of light. Inside the bubble, the laws of physics would be rewritten. Chemistry would stop working. Atoms would fall apart. And because it travels at the speed of light, you would never see it coming. One moment you are here, the next you are simply deleted. This is the danger of living in a universe where the numbers don't seem to make sense. We don't know if the floor we are standing on is solid, or if it's about to give way. The ghost in the machine. Let's step back from the invisible energy and look at the invisible matter. Imagine you are looking at a picture of your house. You see the roof, the windows, the door. But when you step on the scale to weigh the house, and it weighs 5 times more than the materials you can see, there is invisible brick and mortar somewhere, hiding in plain sight. This is the crisis of dark matter. Decades ago, astronomer Vera Rubin noticed something bizarre when looking at spinning galaxies. Galaxies rotate like giant merry-go-rounds. Stars at the center move fast, and stars at the edge should move slower. That's just how gravity works. If the edge moves too fast, it should fly off into space. But when she measured the speed, then the stars at the edge were moving just as fast as the stars in the middle. By all known laws of physics, every galaxy in the universe, including our Milky Way, should have ripped itself apart millions of years ago. Why didn't they? Because something invisible is holding them together. A ghost in the machine. Brian Cox often highlights how humbling this is. We call it dark matter. But that's just a fancy label for we have no idea what this is. We can't see it. We can't touch it. It doesn't reflect light. It passes right through you, right now, as you sit there. But it gets worse. Because while dark matter is pulling things together, there is something else, pushing them apart. In the late 90s, everyone assumed the expansion of the universe would slow down. Gravity pulls things together, so eventually the universe should break. But when they measured distant supernovae, they found the opposite. The universe isn't slowing down, it's speeding up. The galaxies are flying away from us faster today than they were yesterday. This is dark energy. Let's break down the budget of reality. Visible matter. You, me, stars, tacos. 5%. Dark matter, the invisible glue, 27%. Dark energy, the invisible explosion, 68%. 95% of reality is completely unknown to science. Imagine a doctor telling you, "We understand 5% of your body, but the other 95% is a total mystery." You wouldn't trust that doctor. Yet, that is our current model of cosmology. The Hubble tension. We broke the ruler. If you think invisible matter is bad, wait until you hear about the broken ruler. In science, if you measure something 2 different ways, you should get the same answer. If I measure your height with a tape measure and then use a laser scanner, the numbers should match. But when we measure the age and expansion rate of the universe, the numbers don't match. This is called the Hubble tension. Method 1. We look at the baby picture of the universe, the cosmic microwave background radiation left over from the Big Bang. We measure how fast it was expanding then and project forward to today using our best physics. Method 2. We look at standard candles, exploding stars, supernovae, in nearby galaxies, and measure how fast they are moving away from us right now. These two methods give different results, and the difference is statistically significant. It's not a rounding error, it's a 9% discrepancy. That might sound small, but in physics, that is a canyon. It implies that our fundamental understanding of the universe is wrong. Maybe gravity behaves differently on massive scales? Maybe there's a type of particle we haven't discovered? Or maybe the universe isn't expanding evenly. Maybe we are inside a bubble of empty space that is expanding faster than the rest. Brian Cox notes that moments like this, when the data refuses to fit the theory, are when big breakthroughs happen. Or when we realize we've been looking at the puzzle upside down the whole time. The Great Silence. We've talked about the physical universe being off, but there is something else missing. Something that should be here, but isn't. Everyone else. This is the Fermi paradox. But Brian Cox adds a chilling layer to it called the Great Filter.
That it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible.
Let's do the math. There are 200 to 400 billion stars in the Milky Way. Billions of Earth-like planets. The universe is 13.8 billion years old. Earth is only 4.5 billion years old. That means there could be civilizations out there that are millions, maybe billions of years older than us. A civilization that old should have technology indistinguishable from magic. They should have colonized the galaxy. Think about von Neumann probes. These are theoretical self-replicating robots. You send one to a nearby star. It mines an asteroid, builds 2 copies of itself, and sends them to the next stars. Even at slow speeds, exponential growth means these probes could map the entire Milky Way in just a few million years. In cosmic time, a few million years is a blink of an eye. So, where are they? We should see their Dyson spheres harvesting energy from stars. And we should hear their radio chatter. We should see the infrared heat signatures of their galaxy-spanning empires. But we see nothing. The sky is dead silent. Why? Brian Cox suggests that the silence might be the loudest sound in the universe. It implies that life is rare, or even worse, that intelligence is a trap. Cox often discusses the transition from single-celled life to complex life. It took Earth 3 billion years to go from slime to multicellular organisms. That suggests simple life is easy, but complex life is incredibly hard. Maybe the universe is full of bacteria, but empty of minds. Or consider the darker option, the Great Filter. Maybe civilizations arise all the time. But maybe, once they discover nuclear power, or AI, or bioengineering, they destroy themselves. Maybe the silence isn't because nobody is there. Maybe the silence is because everyone is dead. It suggests that there is a hurdle, a filter, that stops civilizations from reaching the stars. The terrifying question is the filter behind us? Did we already survive the hard part, becoming complex life? Or is the filter ahead of us? Are we approaching the wall that wipes everyone else out? The holographic universe. So, the constants are weirdly tuned. 95% of the stuff is missing. The expansion rate is broken. And the aliens are missing. Is there a theory that ties all this weirdness together? Yes. And it might be the strangest one of all. Brian Cox has spent much of his career talking about black holes, specifically the information paradox proposed by Stephen Hawking. Quantum mechanics says that information is never lost. If you burn a book, the information isn't gone, it's just scrambled into ash and smoke. Theoretically, if you could track every particle, you could reconstruct the book. But black holes break this rule. If you throw a book into a black hole, it is crushed into a singularity. And eventually, the black hole evaporates via Hawking radiation. According to our current math, the information of that book disappears from the universe entirely. This violates the laws of quantum physics. But if we save the information, it violates general relativity, Einstein's theory of gravity. You cannot have both. One of our two pillars of physics, quantum mechanics or relativity, is wrong. To solve this, physicists like Leonard Susskind proposed the holographic principle. They suggest that the information of the book isn't lost inside the black hole. Instead, it gets plastered onto the surface of the black hole, the event horizon, like a sticker on a suitcase. This implies that a 3D object, the book, can be perfectly described by 2D data on a surface. Now, zoom out. If this is true for black holes, maybe it's true for the whole universe. Maybe our 3D reality, you, me, the stars, the depth of space, is just a projection, a hologram. Maybe the real universe is a 2D surface of data somewhere far away, and we are just the projection of that data. This would explain why the math is so off. It would explain why the universe feels pixelated at the quantum level. It would explain the fine-tuning. We aren't seeing the code. We are seeing the user interface. And if we are a hologram, who is projecting us? The meaning of the glitch. So, where does this leave us? The constants are fine-tuned to an impossible degree. The universe is mostly invisible. The expansion is accelerating towards a dark, lonely future. The math of the cosmos doesn't match our observations. And in a galaxy of billions of stars, we appear to be totally alone. It is easy to look at all of this and feel insignificant, to feel like a mistake in a broken machine. But Brian Cox takes a different view. A view that transforms this cosmic horror into something beautiful. And the fact that the universe is off, the fact that we don't understand it, is the only reason we are here. If the universe were simple, it would be boring. If gravity were slightly different, there would be no stars. If the universe were perfectly symmetrical, there would be no matter, only light. The imperfections are what allow complexity to exist, and we are the result of that complexity. We are the cosmos made conscious, as Carl Sagan said. But we are a collection of atoms that has come together to ask, what are we? The fact that we are rare makes us valuable. Think about the Fermi paradox again. If we really are the only conscious beings in the Milky Way, then we are the only eyes of the galaxy. We are the only things that can feel love, or wonder, or fear. Without us, the universe is just a play with no audience. It is a massive, silent machine grinding away in the dark. So yes, something is seriously off in the universe. See, the numbers don't match. The shadows are full of ghosts. But that mystery is an invitation. It means the story isn't over. It means there is new physics waiting to be written. It means that the next Einstein is sitting in a classroom right now, wondering why the stars look the way they do. The universe is not broken. It is just waiting for us to figure it out. And until we do, keep looking up.